Alright, welcome back everyone, and in this video we are revisiting the forward path of a forward neural network. And in this video we will focus on the different tasks that we usually have, so the regression type problem, the binary classification problem, and the multi-class classification problem, and we'll discuss on what to look out for and what we need to do if we want to generate the appropriate predictions for these types of problems when using a forward neural network. Okay, so just to repeat the content from the last video, this is how you can visualize what is done by a forward neural network for a single observation. When I say observation, I mean like a single data sample which includes multiple variables or realizations of multiple variables from a unit of interest, for instance from a person. So this could be the age, this could be where the person lives, this could be how much the person earns, and so on and so on. And then these input features are propagated through the network, and they are propagated in a way that in the so-called hidden layers, the hidden neurons are generated, and each hidden neuron is generated by combining an affine transformation of the features that you can see here, and then the value that is outputted by the affine transformation is activated by a certain activation function. And this is done for each neuron, and the only thing which creates different values for the neurons is that we will use different weightings, so different parameters that weight the information which is inputted here by the input features, right? So this is like in short how we generate neurons out of features in the layer that we have before. And of course, then once we have all the hidden neurons in a layer, then we can treat these hidden neurons as we treated the input features and use these hidden neurons in order to generate new neurons. And in the last layer, these neurons are called then the features of the output layer, or the predictions, or whatever, how you want to call it. It's important that you understand what it is, right? Okay, so this is how we can write it down mathematically, but we talked about this in the last video. And basically, we can do this again and again and again, always in the same time. The more often we do it, the more layers we will have into a network. But regarding a forward neural network, it is not really recommendable to use more than 2 or 3 hidden layers. That is due to the vanishing or the exploding gradient problem, something that we will talk about later. Okay. But now let us go into specifics depending on the tasks that we are facing. And let us first we will skip between the slides and examples that you can find in the collaboratory file, in the miscellaneous file. So just a silly example without any meaning, without any content, just to make sure that you understand what's happening from a numerical side here. So assume we have like 2 observations with 3 features. So this is given here. So I marked the realizations for the first observation, right? This is 1, 2, and -2. And then for the second person or whatever we are interested in, the realizations of the features are then here given in the second line, all right? So this could be our input data set, a data set including 2 observations of 3 feature variables. And now assume we want to generate 4 hidden neurons. Then the only thing we care about is the dimensionality of the weight matrix that we need. And if our input is a 2 times 3 matrix, and then if we want to end up having a 2 times and how many hidden neurons we want to have, then of course, for instance, in our case 4, then we need a 3 times 4 weight matrix. So if we multiply a 2 times 3 matrix, which is the input matrix with the data, and multiply this with a weight matrix of dimensionality 3 times 4, then we end up with a 2 times 4 matrix. And here again, the 2 stands for each observation. So 1 and 2, 1 is the first, 2 is the second. And 4, like the columns here, then are the realizations of the hidden neurons. So this is why we just sample any random values for the weights here. Don't care about calibration or estimation or anything else. And yeah, let's delete this. And then we just do a matrix calculation. So we calculate x times the weight matrix. And then for create the hidden neurons, we use the rectifier linear unit activation function, so the ReLU function, which is the max, either the value or 0. Yeah, this generates our hidden neurons for the first layer. So just take a look at the values here. So the input is given here with 1, 2, -1, then and 2, -1, and 0.5 for each observation. Now this 2 times 3 matrix is multiplied with a 3 times 4 matrix, which represents the weights. So these are the parameters. This is what we will calibrate at a later stage. We further assume that all the bias values are now 0 for at the moment. Otherwise, this would be additional parameters that we need to take care of, but we don't want to take care of this now. Otherwise, it may get too complicated. But yeah, multiplying the original input with this 3 times 4 matrix then generates a 2 times 4 matrix. So here each row is representing the observation. So it could be person 1 and person 2. And each value here is like the Z value which we have before we activate the values, right, in the hidden layer. And once we activated it, you can see what happens or what is meant by activation with the ReLU function. You can see that all the values that are 0 or below 0 here are set to 0, and all the other values are kept. So basically we only activate values which are greater than 0. And this is this is an example, like for instance, for the first person, the 2 or the 4 hidden neurons in the first layer would look like this, like it's marked here, right? Okay, and now let's switch back to the slides. We need to distinguish. If we face a regression problem, then for each observation, usually we need a single value that is typically unbounded. So any numerical value, for instance, could represent a house price, could represent the rent we are paying, could represent a price for a car, or whatever we want to estimate. And so now we can do the same that you are used to do for a linear regression model. So we treat the hidden neurons from the layer before the output layer as input feature variables, multiply them with parameters. So basically we generate a weighted sum of the hidden neurons in order to generate a single observation for our target variable. And so what we are doing here is we use the affine transformation as we always do, and then we activate it by simply already taking this value. So this means we use the identity function as an activation function. Okay. If we have classification problems, then, for instance, let's start with the binary classification. Or before we do that, let's first take a look at the notation here. So in general, a classification problem, binary or multiclass, includes big K categories. In case of a binary classification problem, we have k is equal to 2, so we have 2 categories. If we have a multi-class classification problem, then k is 3, 4, 5, 10, 100, whatever. So, but it's integer numbers that we usually use to encode the different categories. And in order to make the notation a little bit easier for us later, we do now something which may look complicated to you. We encode the target variable. So we do this by further introducing here binary indicator variables, which are always either 1 if the observation I of the target variable is the specific category. And this means instead of a single value that we have, like 1 or 2, which typically, or 0 and 1, which typically be used for a binary classification problem, And if we have, for instance, like 3 categories, we may think about 1, 2, 3 or whatever. And instead of writing, I don't know, 2 in order to imply that this observation belongs to category 2, we use a so-called one-hot encoding vector, which indicates which category the target variable belongs to. So assume we have 3 categories, and then we need 3 numbers in order to define the one-hot encoding. And now each value is set to 0, except for the category for which the target variable actually belongs to. So assume we have 3 categories, then the target and the actual category is the second category, then the target vector would look like this here. So it's 0 because it is not category 1, it is 1 because it is category 2, and it is again 0 because it is not category 3. And of course we can do this for any number of categories that we have for target variables. Usually one only uses this for classification problems with more than 2 categories, but of course you can also use this for binary classification problems. And then what is typically done, especially when using neural networks for making predictions in case of classification problems, is not to directly generate outputs which correspond to the category. So this means we will not output 2 or 1 or 3 in order to predict that the target variable belongs to category 2. What we will do is we generate predictions. So for instance, for a classification problem with 3 categories, for each observation we will generate a probability prediction that tells us how high the probability is that we believe that this variable belongs to the specific category. So again, if you take a look at this vector here, that means the ith observation. If this number corresponds to the probability that we believe the ith observation is category 1, then this value here tells us the probability that the target observation or that the observation belongs to category 2, and this value here tells us the probability which we believe that this certain observation belongs to category 3, right? So that is why we also have this here written in bold letters to indicate that this is a probability vector. And I always use the lower k in order to indicate the number of the category, and as always I here stands for the which observation we are referring to. So if we have 2 categories, now let's go to this, then it usually suffices to use only a single output value for the prediction, because as we are speaking of disjoint possibilities, and if we only have 2 categories, that means the probability for the one category already indirectly defines also the probability for the other category, right? Because if it's either 0 or 1, then, and the probability, for instance, for this observation belonging to category 1 is 0.6, then the probability that it belongs to the other category must be 1 minus 0.6. So that's the point here, and that is why it usually is enough to generate a single output prediction for each observation. And what we usually do is we interpret this output usually for the probability that the observation belongs to category 1. And it is very common to use, if we have binary classification, the encoding of 0 and 1. So we have, I don't know, black and white, male, female, whatever. This is usually encoded with 0 and 1 for the target variable. And okay, so instead of the regression problem, we now face the problem that we need to meet certain requirements regarding the output value, regarding the prediction for the target variable, because it is a probability. In case of the binary classification problem, it is the probability for being category 1. And probabilities need to be between 0 and 1. They can be equal to 0, they can be equal to 1, but usually what is done to meet this requirement is to take the Z values, so the values which are generated by using the affine transformation of the hidden neurons in order to condense the information to create the weighted sum. And then this value is an arbitrary number, so it's a real valued number typically. And then this value is inserted or is used as an input into another function, the activation function, which is defined here in the range between 0 and 1. And usually we use the called sigmoid function, or which is also the standard logistic function. And this function does not include typically the values of 0 and 1, but that doesn't really matter, because it can create values that are very, very close to 0 or that are very, very close to 1. And the transformation that we have here is then that you can see here. So it's 1 divided to 1 plus and this e up, and then we have minus z here in the superindex. And so for each observation, we do the same thing as for the regression problem, but then the number that we already would use as a target prediction for the regression problem is again inserted here, or is activated by the sigmoid function. Okay, we will take a look at this for our example in a minute, but now let's quickly also discuss how this changes if we have more than 2 categories. So if we have more than 2 categories, we really generate an output for each observation which has the dimensionality of the categorical problem. That means if we're facing a multi-class classification problem with 3 categories, then for each observation our network will generate 3 values. And each of these values will be interpreted as a probability for being category K. And so now we have, in comparison to the regression type problem and the binary classification problem, the dimensionality of the weight matrix that we will use from the last hidden layer to the output layer will have a different dimensionality. And what's also, but similar to the binary classification problem, is that each of the probability values needs to be between 0 and 1. And now in addition, because it's again, we have disjoint categories, but the sum of all the probability predictions for a single observation needs to sum up to 1. So that is why we use a different activation function, comparing to the binary classification problem, which you can see here. It is the so-called softmax function. So basically what it does is that in the exponent we have the specific set value which corresponds to the certain category. So using the exponential function here generates values that are higher than 0. And now to normalize them, that they are also that they sum up to 1, we build the sum over the all these values. So in the exponent, all the set values for each category. But we will take a look at this at a later stage with examples. But using this function will meet the requirement that each of the probability estimates, so for the ith observation, we will generate probabilities for each category that are between 0 and 1, and that sum up to 1 if we sum over all the probability estimates. And this means that we need a different dimensionality regarding the weights when we generate the output neurons, because for instance, if you have 3 categories, then in our example we have a 2 times 4 matrix for the hidden neurons. 2 because we have 2 observations, and 4 because we have 4 hidden neurons for each observation. And now we will need, if we have 3 categories in the output, we will need a 2 times 3 matrix. So 2 because again, person 1, person 2, but 3 because we need a probability estimate for each category. So this defines the dimensionality that we need for the weight matrix in order to, in order to bring the information from the hidden neurons to the output layer. And if we have a 2 times 4 and we need a 2 times 3, then obviously we need a 4 times 3 in the hidden layer, right? So in order to generate the correct dimensionality for the output neurons. But I hope this will become more clear if we now go to the numerical example. So we started here, and the start here is the same. So we could generate the, no matter with which problem we would face, or no matter which task we would face, to start and generate out of the input information, which are now here again 2 observations and 3 realizations for each feature variable. In order to generate the hidden neurons, we've already seen how we do this. If we want to generate 4 hidden neurons, then we need to multiply this 2 times 3 matrix with a 3 times 4 weight matrix. We assume the bias terms to be 0, and this generates the z values, and then we activated them with the relay function, and we ended up here with these hidden neurons. So now we're in the situation that for the first observation we have these 4 values, and for the second observation we have these values. So now if we face a regression problem, then we have a 2 times 4 matrix, and we multiply this with a 4 times 1 matrix in order to generate a 2 times 1 vector or matrix, and here then each, so 2, so 1 and 2, so for each observation we have 1 value. And if we would do this, then we do it like this. So we would have here the weight matrix for the prediction in order out of the hidden neurons to generate the output neurons. Again, we set the bias values, we assume them to be 0, so we do need to take care of them, and we do not really need an activation function, but what we really do is you use the identity function here. So already the affine transformation is enough to generate out of these 4 hidden neurons the prediction which would be given here. Yeah, the numbers, the values here, they really do not care. More about to show you regarding the dimensionality, what you need to take care of, or you at a later stage you will not directly need to take care of, but I think this is important to understand what happens here. And so this is why we always randomly draw any numbers. So now if we would have the binary classification problem, instead of any numbers here, I mean, this is by a coincidence here that they are really between also, or they're already between 0 and 1. We do not did this here on purpose, that's a coincidence. But if we really need to do this on purpose to generate output values, a single output value for each observation, which corresponds to the probability for the target variable being category 1, then we would do this exactly the same thing as we've done here for the regression type problem, but these values that you can see here are activated by the sigmoid function that you can see here. And this would generate the probability predictions. For each observation, we have a single probability prediction. And so here, for instance, the probability for observation 1 being category 1 would be approximately 0.49. Okay, and then last but not least, and this is a little bit more complicated, but not that much. If we now have we now need 3 values here instead of only a single value for each observation, and these are again probabilities and need to sum up to 1. Then, as I said before, we need a different dimensionality, which makes out of the 4 hidden neurons 3 neurons for the output layer. And if we have a 2 times 4 matrix and we multiply it with a 4 times 3 matrix, which includes the weights, again setting the bias values to 0, then this generates a 2 times 3 matrix. But if we only do the matrix calculation here, then these values are arbitrary values, any real valued numbers. So what we now do here, and do not worry about the definitions of the function and so on, I just did this here manually. Usually we will have well written and efficient functions to do these calculations. But now if we activate the values that we calculate here via the softmax function, then we get the probability estimates. So the set values for the output values, so these are just 3 real valued numbers, and each value corresponds to the probability estimate for the category. But in order really for it to be a probability estimate and to meet the requirements that we have, we activate them in the softmax function, and then this results in a vector for each observation. So for instance here, this number would represent the probability for the first observation being category 1. This number here would be the probability for the first observation being category 2, and so on and so on. Okay. I hope this helps. For me, it always helped, especially for me, it helped or it shaped my understanding in a positive way. Thinking about the dimensions that I need regarding the weight matrices in order to generate the dimensions that I need to output or that I need to produce in order to make reasonable target predictions. And you need to become familiar with this. This is something you do not really need to take care of by yourself when we are applying the models in practice to real data. So do not worry about that too much, but I hope it helps for your understanding. At a later stage, the only thing we need to take care of, that the only need to define manually, is the shape of the input data. So the dimensionality of the input data is something that we need to define, but then the models we will use later, they automatically understand how to set the dimensions of the weight matrices in order to produce the desired output. So this is really just for your understanding and nothing that you really need to do by hand, by yourself, if we really work with real examples. Okay. But yeah, just I think the most important parts so far are really understanding that we again and again and again always we will use what I call the affine transformation. What is meant by this is the formula that you are used from linear regression models. So just let me skip to this. So this is the affine transformation, and basically this means we have a weighted sum of neurons and add a constant value, which is the bias value here. And you need to know that the neurons is something that gets calculated or that gets inserted into the model by the data matrix. And the weightings and the bias term is something which is, as you can see in my example, it typically is initialized randomly, but then later is calibrated by an optimization procedure. But this is not something that already exists, and this is not something that you really need to think about. These are at first random values, which then get refined by an optimization procedure that we will discuss in the near future. Okay. Yeah, I really hope that this helps and doesn't further confuse you. So again, basically the only thing that we really do is out of neurons, because these are all already neurons, are input neurons, we generate other neurons, and we always do this by using weighted sums and activation functions. And then regarding the output, we need to take care, think about which type of output we need. For a regression problem, it's just a numerical number. For a binary classification problem, it is usually a single probability estimation, which corresponds to the probability for being category 1. And for a multi-class classification problem, we need so many numbers for each observations that we have categories, and each number will be interpreted as the probability for this observation belonging to category K. Okay, so in the next video we're going to start and think about how to calibrate these parameters that we have, so the weights and the bias terms, and yeah, how to do this for each different form or task that we have, so regression type problems and classification problems. Take care and see you in the next video.